Hello children, welcome back to the channel. Today we will be taking up the important topic of principle of conservation of mechanical energy. Let's start by assuming that there is a body of mass m and a force F of x on it along the positive x direction. So this force is going to displace the object and along the x-axis, and it will end up at say this position. Let's say this displacement is delta x, a small displacement we are considering. Then from the definition we know that change in kinetic energy, which is equal to the work done by the force, will be given by f of x dot delta x, right? However, since the force is along the x-axis and the displacement is also along the x-axis, so we can say this is equal to fx delta x. Also, in my previous video, the last video that we have discussed, that I have published, we have discussed that in case of conservative forces, what we have is that delta U, that is change of potential energy, can be given by negative of force into displacement. Why? Because conservative force was given by du by dx, or for small displacements du delta u by delta x minus of this. So cross multiplication will give us this, which means that 1 and 2, if these are equations 1 and 2, it simply means that delta K, change in kinetic energy, must be equal to negative of change in potential energy, right? Or we can say that delta K plus delta U, so change in kinetic energy plus change in potential energy of the object will be 0. Or we can say, taking delta common, K plus U, change in kinetic energy plus potential energy will be 0. So change in kinetic plus potential energy will be 0 means it will simply mean that the sum of kinetic energy plus potential energy is a constant. So in case of a system where there is no external interference, in other words, in case of an isolated system, what we get is that the total mechanical energy, kinetic energy plus potential energy, remains constant or remains conserved. It doesn't change. This is known as principle of conservation of mechanical energy. That net mechanical energy of the system will remain conserved. It will not change. Okay, we can simply write this as, say if Ki is the initial kinetic energy of the system when the force was applied, and Ui was the initial potential energy, then this is the initial net energy, total energy. This must be equal to the final kinetic energy plus the final potential energy. Total mechanical energy, if we call this E initial, equal to E final. Initial mechanical energy, total mechanical energy, is equal to final total mechanical energy. Now let us say if this holds for motion under gravity, because we have already said that gravitational force is a conservative force in our previous video, in my previous video. If you haven't seen that video, the link will be given in the description below, so you can please refer to that. So to see whether principle of mechanical energy holds for an object under gravity, let's assume that the object of mass m was initially at a height h from the ground level. Okay, it is released from there, its initial velocity is 0. So if we release the object from a height h, it will move under gravity, so it will accelerate, so it will get a velocity, or in other words, it will gain kinetic energy as we move closer and closer to Earth. The moment it reaches the Earth's surface, the velocity and hence the kinetic energy will be maximum. So let's first consider the case at A. When the object is at A, point A, what is the total energy? Total mechanical energy. It is the sum of the kinetic energy at A plus potential energy at A, right? Now what is the kinetic energy at A? Since the velocity is 0 here, so half mv square, v is 0 here, so it will be 0. So this will be equal to 0. Whereas potential energy will be at a height h, so it will be mgh. We already know this. So total mechanical energy at A will be mgh. This is equation number 1. Now let's consider that the object has moved under gravity and it has reached this particular point level. Say this is level B, which is at a distance or drop of x from here. Or if you consider from ground, this height will be h minus x, right? So let's consider the total energy, mechanical energy at B, point B. So first thing we need to find out that since the object is now moving downwards, so it will have gathered certain amount of kinetic energy, or in other words, it has gathered a free fall under gravity, so it has gathered certain velocity. So at B, let's say velocity is v dash. So to find the kinetic energy, we need to first find v dash. How do we find v dash? We know that the object has moved through a distance of x under gravity. So if we apply the equations of kinematics, then we can find that v dash squared minus u squared, initial velocity, must be equal to 2g into this distance, right? Since u square is 0 or u is 0, so u square will be 0, so we have v dash squared equals to 2gx, right? So kinetic energy at B will be half m v dash square. Substituting the value of v dash from here, we get half into m into 2gx. So we have mgx. And what is the potential energy at B? The object, when it reaches B, the height has become now reduced to h minus x. So the potential energy will be mg h minus x. So the total energy E at B will be sum total of kV plus UV, that is kinetic energy at B plus potential energy at B. So what will be the sum? It will be kinetic energy is mgx plus mgh, we have opened a bracket here, minus mgx, which is equal to mgh. This is number 2. Equation number 2. Now let's consider the object has moved and moved all the way and has reached this point C here. Now what are the considerations? Now what we have found, we'll find is that at C, let's say the velocity has now become v. So again, using equation of kinematics for free fall from A to C, we can simply say that v square minus 0 square must be equal to 2gh now, because the entire height has been traveled by the object. So v square is this implies kinetic energy at C. This point will be half m into 2gh, which is equal to mgh. And potential energy at C, mg into 0, because the object has now reached the ground level, so height becomes 0, so it is equal to 0, which means total energy at C, kinetic plus potential energy, will be equal to mgh. So what we have seen is that the total mechanical energy at the top of the mark at point A, at an intermediate point at point B, and at the final point C on the ground level, all these values are equal. That is to say, E at A equals to E at B equals to E at C. So total potential energy, or sorry, total mechanical energy of the free falling object is constant throughout its entire path. which is a proof to the principle of conservation of mechanical energy. Okay, alright, now let's move on to an important topic of potential energy of a spring. Now, from our experience, we have seen that if you have a spring and we try to extend it, it wants to come back to its original position, right? So if I extend the spring towards say positive x direction, what will happen? It will tend to come back. So a force is developed in the direction to the opposite direction of the displacement. This force is known as the spring force. So this force will try to restore the spring to its original position. Similarly, if I compress the spring also towards negative x direction, what will happen? A force will develop in the opposite direction, that is to say in the positive x direction, so that it wants to extend the spring to its main position, to its comfort position, that is at the position where there was no force applied to the spring. This particular property of spring is explained with the help of Hooke's law, which says that whenever the spring is extended or compressed, it will develop a force, restoring force against the direction of the motion of the spring. That is, whether it's extended, then it will be towards the main position, the force will be opposite to the displacement, and if it's compressed also, the force will be opposite to the displacement. This force Fs, spring force, by Hooke's law is proportional to the magnitude of the displacement. This is Hooke's law, H-O-O-K-E, Hooke's law. Okay, however, since it's a force in the opposite direction of the displacement, we will have to put the negative sign here. This will give us that the spring force is equal to some constant multiplied by the displacement. This constant of proportionality is known as the spring constant. Now, clearly, the spring constant will have the dimensions of force by displacement, that is force per unit length. So the unit of K is going to be in SI Newton per meter, and its dimension is going to be M1 L 1 minus 1 0 T inverse 2. Okay. Now, when we extend or compress the spring force is going to do work, or work is going to be done against the spring force. How much work will be done? Say, since this force, spring force, is dependent on x, so it's a variable force, it's not a constant force. The force's magnitude will change with the displacement x. So we cannot use the constant force terms here, we will use the variable forces terms. That is to say, if for a small displacement dx, spring force can be considered to be constant. That is, we take such a small displacement so that the spring force remains practically constant over it. Then Fs into dx, of course they are in opposite direction, so minus of this, because the angle between Fs, spring force, and dx, say if dx is in this direction, Fx will be this direction, so angle is 180 degree or pi, so F dot dx will be minus F dx, right? So we put it this way, dw, small elemental work done, will be equal to Fs dx, which is equal to minus kx dx, because Fs is taken as a vector, but when we take the actual value, since it's opposite to the direction of the displacement, so this Fs equal to minus kx, it will be in the opposite direction. Okay, so what we get is work done by the spring will be minus kx dx for small elementary displacement of x. So what will be the total work done, Ws, when we displace the spring from its initial position, say xi, let's say xi to x final. If we extend the spring from an initial position of xi to the final position xf, then what we have to do, we have to integrate the entire equation from xi to xf, as was the case with variable force, the way to find the work done by variable force. If you haven't seen my video on that, please refer to the link below where I have given the refer to the description where I have given the link to the video where this has been discussed already. Is equal to minus kx dx, or we can say minus k x square by 2 xi to xf, which will give us that the work done by the spring force is Ws equal to half k xi minus half k xf. Work done by the spring force is the square of that, half kxi square minus half kxf square, the final position, right? So the work done we have seen is dependent on two things only. What was the initial position and what is the final position? We have already discussed in our previous video that if work done by a force depends only on the initial and the final position, then the force will be conservative force. So spring force is conservative. Now, if we consider this is just work done by the spring force, and the spring force as we have seen is always opposite to the displacement. So basically, what we are saying is that work is done against the spring force. So whatever external force has been applied will do certain amount of work W, which say W, that is the will be equal to minus of Ws, right? And this W will be stored as the change in potential energy of the system. Okay, so this spring force or work done by the spring force or negative of work done by the spring force is the amount of work done by the external agency. So what is negative of spring force, work done by spring force? We can find it from here. It is half k x final square minus half k x initial square. Okay, now let us consider, let's say we started at the mean position when there was no extension, which means xi will be 0. There is no extension, we are at the mean position of the spring, so there is no extension, and that's why our extension or compression, so xi is 0, and we have extended the spring or compressed the spring through a distance of x. The final extension is x or this compression is x. Under that condition, this equation will give us delta U, which is equal to U final, right? U final, which is at displacement x, minus U at mean position, must be equal to half k xf square. Xf is x here, so this is equal to half kx square minus kxi square. Xi is 0, so this term will be 0. So potential energy that will be stored in the spring when it is extended through or compressed through a distance of distance of x will be given by half kx square. Now if we take minus du by dx for this, why we are doing this? To see whether it is actually conservative or not, because we know that for conservative force is given by negative gradient of potential energy. Refer to my previous video for this. Okay, du by dx minus du by dx will be minus d dx of half kx squared, right, which will be minus will be there, half k will come, so dx squared by dx, which will be twice x, which will be minus kx, which is equal to the spring force as we had found here. So we have established that spring force is indeed conservative. So we have found that spring force is a conservative force. So what we can say is that principle of conservation of mechanical energy must hold good for spring forces as well. And we are going to make use of this in the following analysis. So what we are going to try to find out now is that, let us say a spring is extended or compressed to a maximum distance of xm. That is to say, we have a spring here, right? This is its mean position, and this is xm minus xm, and this is plus xm. So maximum displacement on either side is xm. Okay. Now, when the spring is at the maximum displacement, what is happening here is that if something is tied to the end of it, and we compress the spring to this particular point, we do not compress it any further, which means that at this particular point the spring is at rest. We release it, it will, because of the spring force, it will move in the opposite direction, start accelerating and get to main position, and then it will start extending. When it starts extending, what will happen? The spring force will start applying the opposite direction, and so the spring force will slow the spring down, and it will go up to a maximum distance, positive xm, where it again comes to a rest. And then because of the spring force is there, which will now, because the spring is extended, is in a negative x direction, it will try to compress the spring. It will come to the mean position, it will already have certain velocity, so because of the inertia it will still keep on moving and coming back to the maximum negative position. So what will happen? The spring will keep on oscillating between the maximum extreme positions through the mean position. Okay, so at this extreme position, at maximum compression or extension position, we must have velocity of the spring or the object here, the tied to the end of the spring, will be 0. So the kinetic energy will be 0, and the potential energy we have just found is equal to half kxm squared, which means that total spring force E, which is k plus u, will be equal, total energy of the spring will be equal to half kxm squared. Okay, now let us consider any position. Say, let us consider an intermediate position where, let's say at x, a random position. It could be positive or negative x, because we are considering the energy concerns and we have x in square, so both the cases the result will be same. Say, let's say this is x, at a particular displacement. Now at this particular x, what will be the total energy? Definitely this is xmc. Ex will be equal to k at x plus u at x, right? What is k? We say k is half m v squared, where v is the velocity of the spring at this particular point at the extension of x during its path. Okay, we do not know, but we know that that will be certain velocity, and so we call this v. And what is ux? Ux is half k x squared, because the extension is now x, or the compression is x right now. So because of conservation of mechanical energy, this Ex must be equal to Exm, which will give us that Exm is half Kxm squared. So half Kxm squared must be equal to half mv square plus half kx square. So we can get the halves here, and so we have mv square equal to k into x m square minus x square, right? So we have v equal to k by m into x m square minus x square, whole thing divided by, whole thing under square root. So velocity of a spring which is oscillating and whose with a mass tied to the end of it. The spring is supposed to be massless, so the entire mass is here. So this mass is mc. Then its velocity will be given by this particular equation. Okay. At any point, given point, x in its path. So we are interested to find that what if x equals to 0? When x is going to be 0? When there is going to be no extension or no compression at the mean position. That is to say, at mean position. So x is 0 means this term will be 0. So what we will have? V will be equal to k by m, whole thing under root, and then xm square under root, so it will come out as xm. So this is maximum velocity that is possible, because when x is 0, this term will have the maximum velocity xm minus xm square minus x square. X is 0, this will be the maximum value of this bracketed term. So velocity will have the maximum value when x is 0, or the spring or the object will be having the maximum value at this particular point, and its value will be given by square root of k by m into xm, where xm is the maximum extension of the spring. This maximum extension or compression of the spring. So these two are very important equations, and we have used the principle of conservation of mechanical energy to arrive at these equations. In the next video, we will start with certain application of or certain problems related to spring forces, and then we'll move on from there. Thank you.